Okay, engineers, now let's see what is the definition of the Laplace transform. Okay, we are going to request the Laplace transform to be linear, and we already saw that before. Okay, the definition of the Laplace transform is something like this. Is the integral from 0 to infinity of exponential minus st times f of t differential of t. That is a definition of the Laplace transform. Okay, on the derivatives and the integrals, they have symbols. This is the symbol for the derivative operation, and this is the symbol for the integral. Now, what is the symbol for the Laplace transform? The symbol is going to be something like this. Laplace transform of f of t, like that. Alright? So this is the symbol of the Laplace transform, the operation. Okay, so what you are going to have is a tortillas machine called the Laplace transform, like this, the Laplace transform. So you are going to throw f of t and you are going to get something. Okay, what is that something? Okay, now, because the Laplace transform definition is actually an integral, well, here the integral, the variable of the integral is the t, okay? So this is from t equal to 0 to t equal to infinite. Okay, so when you solve this integral, what you are going to do later is that you are going to replace the upper limit minus the lower limit. So that means that you are going to set t equal to infinite and then t equal to 0. So the values of t are going to be defined. So what is the only variable that is not defined? The s. Alright, so it's going to be free. So in the end, what you are going to get here out of this is something that is only function of s. By the way, engineers, I don't write the s like we usually do, because my s is very confusing with the number 5. So for this and for this course, this is the s. Alright? To not confuse with number 5. Now in the book, you will see the number s, the normal s. Now it's up to you if you want to use this symbol or the usual s. Okay. Now, so the only variable that survives here is the variable s. Okay. So, but the transformation is f of t. So what we are going to use is capital F. So meaning that you have transformed this function from here, and this is capital F of s. Now that is a convention in the book. If you are in the t domain, then you use f in small letters. Now, if you make the transformation, what you are going to get out of the tortillas machine is capital F of s, right? Referring to the same function, but now one is up here is the t domain, and down below here is the s domain. All right, so that is the definition, engineers. Again, so here is the f of s is going to be the Laplace transform of f of t, and that is equal by definition integral from 0 to infinity exponential minus st f of t differential of t with s greater than 0. Now, why greater than 0? Because in the end, engineers, this integral is actually, because it's undefined, is the area under the curve. Alright? This is the area from 0 to infinite. Alright, now, the exponential of minus st is something that is going to go down. Alright? So you have a restricted area. Now, what happens if the exponential is positive? Here, what happens if it is positive? Then the area becomes infinite. So we cannot calculate that. Okay, so we are going to request this number, meaning that the exponential is going to be exponential negative in the power. So we have a defined area. Okay, engineers, so what we are going to see here is, now let's test if it is linear, all right? Now, the first thing to do is, what is the Laplace transform of 0? Well, according to the previous class, the result must be 0, because The 0 is the same no matter in which domain you are. So if you throw here 0, you should get 0. If you transform $0 into pesos, you should get 0 pesos. That is expected. Okay, let's see what happens if that happens. Okay, because we don't have formulas yet, we are going to develop the formulas. We don't have the formula, so we have to use the definition. So it's going to be the integral from 0 to infinite exponential minus t. And this function, f of t, becomes 0 times 0 differential of t equals to 0. So whatever you have here is going to be inserted here. Could be 0, could be t squared, could be the sine of t, could be the exponential of t. Okay, no matter what you have here, it is going to be here. Now, how much is 0 times the exponential? So that is the integral of 0 from 0 to infinite differential of t. Now, what is the integral of 0? Well, it's going to be a constant, but when you do the upper limit minus the lower limit, then it's going to be 0. Because in the end, there is no area. It's just 0. Okay, so the Laplace transform of 0 happens to be 0. So this is the first thing of linearity. Looks linear. Okay, now that is the first thing to check if it is linear. Now the second thing to check if the Laplace transform of f of t plus g of t is equal to the Laplace transform of each one of them plus the Laplace transform of g of t. So no matter if you do the transformation together or separately, you should get the same result. Now, I'm going to include plus or minus, all right? Okay, the Laplace transform of f of t, by definition, is the integral from 0 to infinite exponential minus st, f of t, differential of t. And the Laplace transform of g of t, by definition, is going to be the integral from 0 to infinite exponential minus st, and then g of t, differential of t. So remember, whatever you have here goes here. Okay, what happens if you have the Laplace transform of the addition f of t plus g of t? Okay, by definition, is the integral from 0 to infinite exponential minus st times f of t plus g of t. I'm going to handle right now just the positive. I will add the negative later, but let's do what happens here. Now, the multiplication, this is normal multiplication, is going to be this times this and this times this. And the integral, the integral is distributive, so you can do the integral of this plus the integral of this. So this is going to be equal to the integral from 0 to infinite exponential minus st and then f of t differential of t, okay? Plus the integral from 0 to infinite exponential minus st and then g of t, there, differential of t, all right? Okay, now what is this? This is exactly the definition of the Laplace transform here. And what is this? That is exactly the definition of the Laplace transform of g of t. So that means that the Laplace transform of f of t plus g of t is equal to these two guys, the Laplace transform of f of t plus the Laplace transform of g of t. Okay, so we have proven that no matter if you do it together or if you do it separately, they happen to be the same. Now it doesn't matter if it is positive or negative, positive or negative, positive or negative, it doesn't matter. All right, now we have, so looks linear because of the 0. Now because of this also looks linear, but we have something missing. The Laplace transform, the last thing is the constant. The constant, you can take it outside the constant, so the Laplace transform of k f of t, k being a constant. By definition, this is going to be the integral from 0 to infinite exponential minus st, and then times this goes here, k f of t differential of t. Now, because here you have multiplication, this multiplication, this multiplication, then this k can be taken outside. Now, This k is not dependent on the t, so the k can be taken outside of the integral. So this is going to be equal to k integral from 0 to infinite exponential minus st f of t differential of t. Now, what is this? Well, this is the definition of the Laplace transform of f of t. So that means that the Laplace transform of k f of t is equal to k times the Laplace transform of f of t. Okay, because we comply with this one, and with this one, then it is linear. Now, why do we want linearity in engineering? Well, because we expect that if we do the transformation together or separately, we get the same, just like the currency example. Or if you happen to have 0 in one domain, you expect to have the same 0 in the other domain. So that is expected. 0 pesos in Mexico, it will be equal to $0 in the US, or 0 euros in Europe, whatever, all right? And the k, what happens here, we expect the k is that if you do the transformation of 3 times $9, or you do this transformation of the same amount times 3 in pesos. So it doesn't matter in which domain you are. The k times here in this domain should be the same k in the other domain. Okay, so that's for the Laplace transform definition and showing that it is linear. Next video we are going to cover what are the formulas of the transformation of the Laplace transform, because just like in the derivatives or the integrals, you don't do the definition. What you do is just the application of the formulas, all right? So let's demonstrate those formulas. See you on the next one.